Hello everyone, welcome to PYNQ FPGA development with Python and VIVADO. We are from Logictronics and Digitronics Nepal. So today we are in section of creating PYNQ overlay. So we are going to create user-defined or custom type of overlay, that is VIVADO based design, and implement that design on PYNQ FPGA. So in this section we have the lab sessions along with theoretical session of topic. So in the first topic we have the PYNQ overlay basic. So we will talk about the what exactly the overlay is, and we also have lab sessions. So in this lecture we will have lab 4.1, which is creating addition and multiplication based overlay. That means we are going to create overlay of addition and multiplication application. That means which can add and multiply two different numbers. We will use VIVADO high level synthesis and IP integrator, and as usual we will also use Jupyter notebook. So we also have lab 4.2 of creating custom overlay for layer control, that is GPI controlling, in the next session, which is lab 4.2, and lab 4.3 also accelerating Python function on PYNQ. So for this video session we will cover topic 1 and lab 4.1. So let's go for PYNQ overlay basics. So basically overlay is like custom type of design or any type of design which is the implementable design on programmable logic. So basically you are familiar with PYNQ FPGA architecture. So PYNQ FPGA consists of processing system and programmable logic. So if we want to implement any design on programmable logic, then that can be called as overlay. So overlay configure the necessary blocks and set of like GPIOs, and we can call that overlay with Jupyter interface, and we can like instantiate, or we can set or configure overlay as our requirement. So it just work is the available or built-in bitstream or overlay of PYNQ operating system, PYNQ OS, which you download from pynq.io. So basically there is already default OS, so we just want to add our bitstream inside that OS so we can utilize our design. Other things will be same. That means the operating system will be exactly the same, just we will change the bitstream as our requirement. So basically in overlay design, so it can cover different like set of input output segments or elements of PYNQ FPGA. So you can have GPI based overlay, you can have like different interface based overlays. So you can utilize that, and you can also instantiate the soft processors. And basically in overlay design you will have the like different blocks, processing system or the processor, and other interconnected AXI building blocks or peripheral interconnection blocks. So these are the things which you need to have. And now we are at lab 4.1, so which is creating the custom overlay for addition and multiplication. So in this session we will follow VIVADO HLS. In the first we will design the basic VIVADO HLS based application with or for the application of addition and multiplication of two numbers, and we will synthesize that design in VIVADO HLS. We will like export the RTL, and export means VIVADO HLS can export design to IP integrator, and in IP integrator we will create the new block design and integrate HLS IP with Zinc processing system and other few peripherals. Then after we can follow the VIVADO IP integrator based like synthesis, implementation and generation options. So this is the basic code. Actually this code is inspired from the PYNQ overlay tutorial. So our session is inspired from this tutorial. So you can see the overlay tutorials from this link, that is overlay design methodology of PYNQ read the docs.io. So it have the addition, so we just add multiplication. So two applications will run on our project, so the things will be similar. This is our high-level synthesis source for addition and multiplication. So this is the main functions, which is void add mul for addition and multiplication. We have inputs like a, b as inputs, which are defined in integer format, and this a, b values or the inputs will compute it for addition and multiplication results. So we have the C is for like addition result, and M is for multiplication results. And this is inspired from the PYNQ.io overlay tutorial. So you already see that link. And we have the ports instantiation for SXLite interface. So A, B, C, M are instantiated for different ports, and all the non-necessary like ports are drawn off. So the first line will drawn off the other ports which are not necessary for us, like basic interrupt and other things will be drawn off, and it is just bundling for slave XC light type of IP, and the operation is here: C is equal to A plus B and M is equal to A into B. So this is the very basic operation, just like is the PYNQ overlay tutorial. So we will write this algorithm on high-level synthesis. Then we will follow these steps for like this is the completed step for designing with high-level synthesis. So you can just go to high-level synthesis, create the new project, like add the new type of source, add mul.cpp, or you can just add the already available source, and you can select the part of PYNQ FPGA. So part is XC70020 CLG 400-1. This is the part which we will type on high-level synthesis, and the part is same for Z1 and Z2. And you can see the sources option there, where you can just edit the addmul.cpp, and after you edit the source file, then you can do the run C synthesis, which will synthesize the design, and we'll also get the synthesis report for analysis. And after the synthesis is complete, we will do the export RTL, and which exports the our high-level synthesis design to VIVADO IP Integrator, so we can do the process on IP Integrator. So this is the step first, and after that we will see the addresses is shown here, and we can go for the next step, which is actually VIVADO IP Integration. Actually, we also revise these steps in the later session while we do these steps in tool, specific tool, high-level synthesis tool, or VIVADO IP Integrator tool, and we will follow this. This will be our block design at the end of VIVADO IP Integration, and we will follow these steps for generation. After that, we will connect our PYNQ FPGA board and copy our bit stream as well as block design to the PYNQ FPGA and explore our design with Jupyter interface. And currently we are connected our PYNQ FPGA on the network, so we will access through PYNQ:1990 instead of this link. This link is for like connecting PYNQ with the Ethernet cable or the LAN interface. Now we are connecting our PYNQ with the router, so we will connect with PYNQ:1990, and this is the code which we will run on our PYNQ FPGA. So we will call the like bit streams and instantiate the IP and other things. This is the example code. So let's go for the VIVADO HLS project. So let's start from creating a new project, and we already show you the source, so we will follow that source. Let's browse, and we can place any name here. So let's do next, and let's create the new file here. So let's place name is addmul.cpp C++ file, and let's instantiate, or let's just keep the top function name, which we will have addmul. So let's do next, and we don't have any test bench for now. We are not going to simulate or see the results on test bench or the simulations. So we will just have synthesis in VIVADO high-level synthesis, then we will cover the export RTL. So let's search for the PYNQ Z1 or Z2 part. Actually, we have not instantiate the Z1 board file or Z2 board file here. So we will just search using the part number. So this is our part XC7J020 CLG400-1. Let's click on OK. Other settings are as default, and let's to finish. And let's again went back for the source file. So here is the source, and we'll also attach this source on the attachment, so you can get the source from the attachment if you don't like to type. Else you can just type it. Now we will just going to copy it. Our high level synthesis tool is just open up. So let's expand this source file from the Explorer, and you will get edmul.cpp, which is our C file, basically C++ file, where we are going to paste our code, that is the algorithm for addition and multiplication. So let's just paste it here. Let's just save this design. So we can just do Ctrl+S, or we can just save it from here. Now it is good. And let's run C synthesis. First of all, we will run the C synthesis, then we can run export RTL. So our synthesis has been successfully completed. So now let's go for export RTL. So you can see the export RTL option here. Let's click on it. It will ask for the language, which language you want to export with. Any language like PSDL or Verilog, any of one works well. There is no any issue. After export completes, we will start the VIVADO IP Integrator program. So while we synthesize design, we will see this type of synthesis report, which includes the timing summary and a resource utilization summary. So these are the things which we can see from the synthesis report. And this synthesis folder includes all the sources of PSDL, Verilog, System C, which is converted from high level synthesis, that is this code. This code has been converted to PSDL, Verilog and System C by this tool, and it also produces some reports which we getting from here, from synthesis report. Our export RTL for option is successful. So now let's go for VIVADO, and we can even revise our steps from here. And another thing we can see, we can just go to implementation. Inside it there is IP, drivers, edmul v1 source, and edmul sw.h. So we can get the address of like A, B, C and yum. So these are the variables which we have, A, B, C, yum. So all the variables are instantiated with some addresses. So 0x10 is for A, which is integer A, 18 is for integer B, 20 is for integer C, which is the pointer by reference, and the 24 is for 28 is for yum. So these are the addresses which we are going to use on Jupyter notebook. So our VIVADO is open. Let's create a new project, and let's click on RTL project, and let's also check this option. Let's do next, and let's again search for the parts. So this is the parts XC7J020 CLG400-1. While if you install the boards, then you can just go for boards. We have installed the boards, but you might not have, so we are searching with parts. So let's do finish. So our VIVADO has been opened up. Let's go for the create block design, place the default name, and before adding our IP on the block design, let's go for the setting. First of all, we have to import, or we have to set up the IP repository option. We have to select the IP folder, and it will sync. It will automatically scan for IP. That is, add-mol is our IP, and we can do apply. We can do OK. Now we can add this add-mol IP in our block design and integrate add-mol IP with Zinc processing system. So let's click on add IP. We can click add-mol, and we can even add the Zinc processing system. After Zinc processing system added, we can just use the automation. So we have the run block automation. Let's click on it. Use as default, and let's click on OK. Let's also click on run connection automation. Regenerate the BD layout. All the connection is set up as we presented in the PowerPoint. Now we have to validate the design. It is OK, and we can even check the address editor. Address editor basically consists of addresses. This address is utilized on the VIVADO SDK programming, while the Jupyter base interface don't need this address. We will just need the high-level synthesis base address. That is we see on high-level synthesis tool. Now let's go for the sources. Right click on the design one, create SGL wrapper, let VIVADO do. So basically we are just creating the hardware description language wrapper, that is the VSGL or Verilog source file from this block design. So we can synthesize this block design in SDL format. So this is the wrapper, and we don't need any constraint for this design because we don't have any general programming input outputs or any interfaces. Any physical interface is not present here. So we can just click on run implementation, or we can go further for generate PD stream. Let's click on generate PD stream, and it will start from synthesis option. And we can also select the number of processors. Actually in my PC there is no much processors, there are only 4, so I can select any of 4. So let's click on OK. So guys, our PD stream generation has been successfully completed. So let's cancel this option and let's go for PD stream. And we also need the block design tickle file. So let's click on export, and let's click on export block design, and we can export block design on our local project directory. Let's click on OK, and you can also export that block design in your desktop so you can find it more easily. And we already have gone through the project directory, which is add-mol VIVADO. Add-mol VIVADO, we have the block design here, and we also need the PD stream. So PD stream can be found inside runs. Inside the implementation you can find bit file. So let's copy this bit file and let's put it here for now, and let's make both bit file name as same name. So we can just make it design1 add-mol, and we can also rename this tickle file as design1 add-mol. Now our rename has been completed. Now we have to copy this both file, and let's go for PYNQ. Actually we already have connected our PYNQ FPGA with our network, so we can go for /PYNQ /Xilinx. So if you are in like LAN Ethernet cable, then you have to type /192.168.2.99, and the username is Xilinx and password is also Xilinx. And we can see the Jupyter notebooks here, and let's create a new folder here. Like we can create add-mol, and inside that we will paste our bit file and tickle file. So these are the things which we need for Jupyter interface. Now let's go for the Jupyter, and let's go in the home, and we can see add-mol is added here. However, we can also add the folder from here also. So here is also option. Let's go inside add-mol, and we have the bit file and tickle file, and let's add new Python 3 file. So in Python 3 file, what we are going to do is we just utilize the structure stated here. So first of all, import the overlay and bit stream, and import the IP, add the IP, and we will put some value on that IP based functions. Overlay and add mul. Now everything is good. So we are just going to put the value of 4 in A, 5 in B, and we will read the addition and multiplication results. So basically we can just break it, and first of all run this, and in the second we can just run this. So basically we get the addition as well as multiplication result here. So it is based upon our HLS addresses. I will mention these addresses and our main program, and this program is wrapped with processing systems in this block design. So this is everything which we need to know about, and there are other few things which are much more interesting, that is creating the drivers. So you can also explore these drivers, and we can also do the things. So let's just copy this section, and first of all rename this project. Mol is our project name, and we can go for the, and we can just paste it here. We can update our HLS IP name, which is mol b10, and we have the address of 1018 return self. We can have add function first, and we can have mol function. Mol function is utilizing the 28th results, and now we can go for the we can instantiate overlay again. So our bit stream can be initialized on. Now we can use the functions, like we can use add mol. Our addition driver is working but have a little bit issue with multiplication. We can solve that, and we will attach you on the project attachment, so we can find that. Meet you in next session.